this is electric field lines and diagrams. So we're doing a little bit more electric field stuff here. Let me just, okay. Sorry, I was trying to rearrange my paper here, but I think this is as best as I'm going to get it. Okay, this is just to kind of show you, right? We did these in Unit 2 as well with the electric field lines and stuff. You notice that if you have opposite sign charges, they connect and they create this kind of melon-looking shape right here. If you have the lines, two like charges are going to have lines between them that make a diamond shape. I call it a primogem shape because it looks like a primogem from Genshin Impact. Okay, you notice that you get that little diamond shape right here. Okay. Um, and then you'll notice that field lines always intersect perpendicular to the surface of any conductor. So if you have, a conductor outside or where the charge is, or the conductor's in, or the charge is inside of a conductor or something like that, then the lines are always going to intersect perpendicular to the surface of that conductor. Okay. In the case of the left in the case of this left diagram right here, you're going to notice again, they still are forming that melon shape, but you're going to notice the stronger charge has more lines either emanating or connecting to it. So you'll notice that charge 1 is stronger than charge 2 because it has more field lines emanating from it than 2 is receiving. Okay. Positive charges emanate, they shoot out the electric field lines, and negative charges receive them. Okay. And then in this case right here, you're going to see that 2 is now emanating the lines. He's not doing as much though as 1. 1 is pulling in a lot more than 2 is shooting out. And then here, one way that you can tell the stronger charge is of course the lines, but also you can look at where the diamond is, like where the center of that primogem is, and you can see, right here, it's not perfectly dead center. In the example up here, it was dead center, right? The center of that diamond was dead center. Now it's not. It's shifted a little bit more towards 2. So the stronger charge pushes the center of that diamond a little bit closer to the weaker charge. Okay, so that's one way that you can tell stronger charges, weaker charges. Here also you can tell that the melon kind of gets looks more like an onion kind of, and typically the I don't know how to describe it. Like the bulb of the onion is going to be towards the stronger charge, right? Whereas the base of the onion would probably be towards the weaker charge, right? That's probably not a super surefire way of doing it. I mean, use that at your own caution, but this is definitely a more foolproof way of doing it. Okay. Okay. This is just a bunch of examples involving electric field lines. The figure shows two conducting spheres that are very far apart. The spheres have the same radius r and different negative charges shown. At the surface of which conductor is the electric field the strongest? Explain your reasoning. Okay. So I don't even actually need to really look at the diagram here. If I know that E is equal to KQ over R squared, okay. So sphere B has more charge and both have the same radius. Okay, so R squared is same. Okay, and then Q is greater for B. So sphere B is going to have a stronger electric field at its surface because it has more charge. That's more charge that gets distributed. Okay. Okay. Um, Example number 2 is about 3-point charges of equal magnitude, but different signs are arranged in a line as shown. The distance d between each charge is the same. Point x is exactly halfway between the two positive charges. Point y is exactly halfway between the negative charge and the positive charge in the middle of the line. At which point x, y, z, x or y is the magnitude of the electric field greater? Explain your reasoning. Draw electric field lines. Okay, so the positive charges emanate the lines, and they're all equal magnitude. So I'm going to draw, I guess, 6 maybe. I don't know. I'm just going to draw however many, right? You'll notice that Q is going to, emanate these field lines, and it's going to actually oppose, because there's a positive charge right here. This positive charge is going to have lines out here that go away. This should actually probably be curved a little bit that way. Okay. So they form the little diamond between them. Okay. Well, then what you're going to notice is that there's opposite sign charges right here, so they should connect. Okay. So then you're going to notice that what happens is these lines are going to go. Okay. So these lines connect. Okay. And then obviously there'd probably, there's going to be some, lines out here and whatever. Okay. Well, it's important to note that X is going to have 0 electric field. Okay. At X, okay, E field is equal to 0, okay, because um, it is between two same sign charges, okay? And then at Y, the E field is equal to, E field is equal to, I guess I should say greater than 0. We don't know how much it is, okay, because it is between two opposite sign charges, okay? So at Y, you have to have some E field. It doesn't matter exactly how much it is, but you know that it has to have some E field. At X, there is no E field at all because the diamond, in the center of the diamond, there's 0 E field. Okay. Okay. In each case shown below, the distance L is the same. Draw an arrow emerging from point P to represent the direction of the electric field produced by the two charges. Okay. Okay. Well, again, it's important to remember that negative charges are attractive and positive charges are repulsive. Okay, so this is a negative charge right here, positive charge. Positive charge is going to repulse up this way. Okay, we're going to call this, E sub n. The negative charge m is going to be attractive. Okay, E sub m. So then the net electric field is going to go up and to the right. Okay, and it may not necessarily, it looks like it's going to be a little bit more vertical than it will, or sorry, a little bit more up than it will be to the right because this is a stronger charge. It's probably going to look something kind of like this. Okay, that's going to be, I'm going to call this E net. In the other case, okay, you have your positive charge emits a repulsive force going straight down. Not very strong though, because it's only 3 microcoulombs, E sub F. And then G emits a attractive force, and it's a really strong one because this is a strong, relatively speaking, this is stronger than that one, right? So this is going to be E sub G, okay? Okay, and then what you're going to do is you're going to see that the force needs to be a little bit more horizontal, or the net field needs to be a little bit more horizontal than it does vertical. So I'm going to draw it maybe something kind of like this. Okay, E net. Okay. Okay. Let L equal 2 meters. Calculate the magnitude of the electric field at point P. So in order for me to do that, I would need to calculate each field individually. Okay. E sub n is going to be equal to kq over r squared. Okay. And all I have to do is k is 9 times 10 to the 9. Q is going to be, so this is for charge n, 10 times 10 to the negative 6. Okay, and the distance is 2 meters. Okay. When I calculate that out, I should end up getting negative 4,500 newtons per coulomb. Okay. It should actually be positive. Okay. Oh wait, no, I'm so sorry. I was looking at this is the other one. This ends up being 22,500 newtons per coulomb. Okay. And then when you do, that's n. When you do E sub m, that ends up being kq over r squared. So that's going to be 9 times 10 to the 9th. And then this ends up being negative 2 times 10 to the negative 6th. And that's over 2. That one ends up being the negative 4,500. Okay. Okay. And then when you calculate that out, so you have to then Pythagorean theorem it. Okay. And so I would do E net is going to be equal to the Pythagorean theorem of these two, which is going to be 22 or 22,500 squared plus 4,500 squared. I don't need the negative on it because the square cancels it out anyway. And I should end up getting about 22,900 newtons per coulomb. Okay, so you notice that the vertical, and this makes sense because the vertical electric field is stronger than the horizontal. Okay, so it should be pushed a little bit more towards the. Oh, great! Baldur's Gate 3 is ready to play. Awesome. Okay, don't know why it showed. I thought I turned off all my Steam notifications. Okay. Okay. This is okay. So for this one, you're going to do the exact same thing. Okay. E sub f is going to be equal to 9 times 10 to the ninth times 3 times 10 to the negative sixth over the distance L, which is now going to be 6. Okay, and you should end up getting about 750 newtons per coulomb on that one, and that one makes sense because it's a really small number. And then E sub G is going to be 9 times 10 to the ninth times 18 times 10 to the negative sixth over 6 equals, that ends up giving us negative 4,500 newtons per coulomb. So yeah, it looks like it ends up being very, just ends up being the exact same thing as e to the e sub m right here, right? And then when you calculate the net electric field, you're again Pythagorean theoreming it. Theoreming it. Okay. 750 squared plus 4,500 squared. That's going to give me about 4,562 newtons per coulomb. Okay, that's probably more than likely a rounding thing. I don't remember off the top of my head if I rounded that or not, but that's probably just a rounding thing. I probably rounded that one too, if I'm being honest. I round a lot of stuff in this. Okay. Okay. Um, Okay, and then this is the last example for this section is that you've got 4-point charges in the centers of sides of a square. You sometimes see this example where they're in the corners of a square. This is where they're in the center of the sides of the square, okay? So they kind of make a little cross shape, okay? The magnitude of the electric field at point P due to charge L is E, okay? So L applies a repulsive E field on P, okay? So here's what I'm going to do. I'm going to do, blue, green, red, and pink. Okay, so just so I can color code myself here. Okay. L applies a repulsive field of magnitude E. Okay. E sub L. Okay. R applies a repulsive field of 2Q to the right. Okay. So, or sorry, 2E. Okay. And I'm doing this all in terms of the, or I guess it says it's just E, right? So I guess I don't even need the L in it, right? I don't need the L in it, okay? Because if I have double the charge, I should have double the field, right? S is applying a attractive field of E, okay? And then T is applying a doubly attractive field of E here, okay? So all I would have to do to solve this is to figure out this is basically, Pythagorean theorem again, okay? With my height being 2e, this is going to be 4e. So what I can do is I can calculate out Pythagorean theorem, 4e squared plus 2e squared, okay? And then when I square them inside of the root, I should end up getting 16e squared plus 4 E squared, okay? And this ends up being, root 20 E squared. And you can simplify that to just being root 20 E, okay? So that would actually go this way. Okay, it'd actually probably be a little bit flatter than that because the horizontal field is so much stronger than the vertical field. Okay. The magnitudes of the forces required to hold charges R and T in place are Fr and Ft respectively. Which force has greater magnitude? Well, if you notice that R and T opposite each other, they're going to feel the exact same force from S and L as each other, and they are going to apply the same force onto each other. So the two forces should be equal. Okay. Both should be equal. Okay. Um, S and T feel same force from, or not S and T, sorry, R and T. R and T feel the same force from S and L. Okay. And apply same force to each other. To each other. Okay. Okay. The next part is the same thing. Okay, it's the exact same thing, but the only big difference is that we're changing the magnitude of some of the charges. The magnitude of the electric field at point P due to charge A is E. Okay, so this is going to be a repulsive E. B is going to have an attractive 3Q, or sorry, 3E. Okay. C is going to have a repulsive 2Q. Okay. Or sorry, 2E, sorry. And then D is going to have an attractive 1Q, or 1E. Okay. So the net electric field ends up being up and to the left. Okay. And we would see, should be up and to the left, maybe a little bit more up than it is to the left. Okay. And to calculate it, again, Pythagorean theorem, the net horizontal field is 1e, the net vertical field is 2e. So this ends up being root 2e squared plus just e squared, okay, equals root 4e squared plus e squared, okay. And that just ends up being root 5e, okay, because you'll add them together to get 5e squared, and then you can square root both sides, both terms, and you end up getting root 5e squared, and you can take the root of the e, right? Okay. A and C. So C is actually going to feel more force from the other two charges than A will because it's stronger, okay? So C should feel more force. Where's my pen? C should, sorry, I should say F sub C should be greater because C feels more force from other charges because C is stronger than A. Okay? Because C is stronger than A, it should feel more force from the other charges. A and C still exert the same force on each other, but C itself is going to feel more force from B and Q, or B and D. Okay? Okay, and the last part here is more practice with is the exact same thing, right? The electric field at point P due to charge Y is E, so this is going to be the rightmost charge here. This is going to give an attractive field of E. Okay. Z is going to have a oh, my bad. This should be a repulsive field of E. Okay. Z is going to have a attractive field of 2Q or 2E. Okay. W has a repulsive of 4Q, 4E, okay? And then X is going to have a repulsive field of 3E, okay? Okay. So this is going to be 3E and 5E, okay? So this ends up being, let's see, we calculate it out, we Pythagorean theorem it, root 5E, 5E squared plus 3E squared, okay? Okay, and then what's going to happen is we can square everything out. This becomes root 25e squared plus 9e squared, and that's going to, and then we can add those together. That becomes 34e squared. And then you can calculate that out to figure out it's just root 34 times e. Okay? Okay. And then magnitude is required to hold W and Y in place are force W, force Y, respectively. Which one has greater magnitude? We'll take a look at which one's stronger. W is a stronger charge, so it feels greater force from Z and X than Y does. W and Y apply the same force on each other. Okay, so I would say that F sub or F. Why did I draw an E? F W is greater because W is stronger than Y, so it feels more force from X and Z. Okay? Stronger charge. Remember that the force felt by a charge is dependent on its own charge as well. Okay? All right. That is, what was that, section 4? I'm pretty sure it was section 4 because lecture, yeah, section 4. Okay.